So, okay, I'll start now. We're going to discuss today, we'll start in the next set of 5-6 lectures, we'll discuss what's called duality in gauge theories, and on the way we'll understand what do we mean by the word duality in gauge theories. And today we'll start discussing exact duality in pure electromagnetism. And we'll show, we'll demonstrate that in this theory there is an exact duality symmetry which relates electric and magnetic fields. This is what we'll demonstrate. So let's recall Maxwell's theory. Recall Maxwell's theory. Maxwell's theory is given in terms of, in natural units, divergence of electric field is electric charge density, and divergence of magnetic field is 0. And curl of electric field plus rate of change of magnetic field with time is 0, and curl of magnetic field minus rate of change of electric field with time is the electric current. This is the standard Maxwell's theory. Let's consider pure theory. Pure means consider pure electromagnetism, which means no electric charges, which means rho E equal to 0 and no electric density and no current, electric current. Then these equations are simply divergence of E is 0 and divergence of B is 0, curl of E plus dB dt is 0, and curl of E minus dB dt is 0. Let's rewrite this theory, rewrite these equations. Oh, I think I did the so let's rewrite it and combine these into one equation. Divergence of electric field plus I times magnetic field is 0. And combine these two equations as curl of E plus IB plus I times minus I times d by dt of E plus IB is 0. Just rewrite these by combining this set of equations, these two, into one complex equation and these two in one complex equation. Now notice these equations are unchanged under what transformation, which we'll call duality now, under duality transformation, which takes electric field to magnetic field and magnetic field to minus electric field. So this is a duality transformation, and we give it a name D. Or in this combined form, I could write it that E plus IB changes to B, E changes to B, and B changes to minus E, that is minus E plus IB. So this transformation interchanges electric and magnetic fields. Changes E to B, but B to minus E. Or put in this complex form, it changes it by a phase minus I. Now if I do this transformation twice, then E changes one transformation to B and B changes to minus E. So E changes to minus E. That's first transformation B changes to minus E, and second transformation E changes to B. So B changes to minus B. So this tells us D square changes electric field by sign, magnetic field by sign. So D square is same as charge conjugation. So this pure electromagnetism has symmetries, the standard symmetries besides the Lorentz symmetry, because these equations are covariant in the Lorentz transformations. And also they are invariant under conformal transformations. And besides these, pure electromagnetic equations exhibit duality symmetry. In fact, they exhibit a symmetry which is even larger than the duality, this discrete duality that we have described here. In fact, equations, electromagnetic equations exhibit a larger symmetry. How do I see that? larger than this discrete. This is a discrete symmetry. Larger symmetry than discrete duality. And we give that larger symmetry a name. We'll call it a duality rotation. E plus IB changes to exponential I phi E plus IB, phi a constant, arbitrary constant. Phi equal to minus pi by 2 is the discrete symmetry, is one point of the symmetry. Because obviously if I multiply it by a phase, this constant phase, this equation is unchanged, these equations are unchanged. So not only discrete duality, but even duality rotation, where phi is an arbitrary constant phase. Now let me exhibit this symmetry in some slightly different notation. Electromagnetism, the E field and B field can be combined into a Lorentz tensor, which is what we call the field strength earlier, F mu nu. So let me write down that. So combine E and B into an antisymmetric tensor, Lorentz tensor, F mu nu. In the matrix form, it is antisymmetric, so diagonal element is 0, electric field E1 component minus E2 component minus E3 component, E1 component, E2 component, E3 component, diagonal element 0, diagonal element 0, diagonal element 0, and this is minus B3 plus B2 plus B3 minus B2 B1 minus B1. So the field strength F mu nu is this 4 cross 4 matrix in terms of electric field and magnetic field components. Or more compactly, electric field EI is minus F0I, and magnetic field components BI are minus, I think, minus half epsilon I jk F jk. And the same pre-Maxwell's equations written in terms of these tensors is a derivative of F mu nu, d mu of F mu nu is 0, and d mu of F mu nu dual is 0, where F mu nu dual is half epsilon mu nu alpha beta F alpha beta. And epsilon mu nu alpha beta is completely antisymmetric, which means if I change any two indices in that, it changes sign, and with components which are plus or minus 1 and 0, the only with the convention 0, 1, 2, 3 is plus 1. Remember, our metric is G mu nu is 1 minus 1 minus 1 minus 1. Minkowski metric is diagonal plus 1 in the time direction and minus 1 in all the space directions. Written in terms of these objects, discrete duality transformation is f mu nu goes to f mu nu dual, and f mu nu dual goes to minus f mu nu. And the same if I do the d square here, one takes it to f mu nu dual, second takes it to minus f mu nu. So this is restatement of the same objects in covariant notation. This was Minkowski space, space-time. Now I could do this also in the Euclidean space-time, because Euclidean sometimes we should, for some reason, wrote theories in Euclidean space-time. If I did it in Euclidean space-time, then Euclidean. So this is an aside, space-time. F d square is f mu nu goes to f mu nu, one's dual, second dual is plus f mu nu. That's an exercise. Check that in Euclidean space-time d square, d square, this discrete duality done twice leaves f unchanged. Now in electromagnetism there are two quantities of interest. In electromagnetism there are two quantities of interest. One of them is the energy density, and energy density is half electric field square plus magnetic field square. That's the energy of electromagnetic field. Second object is the momentum density. Which is also given a name, Poynting vector, and that object is E cross B. Now let me write them. Oh, write half, put it half. That doesn't matter, twice the Poynting vector. Here I did the right normalization. See, that's why I didn't put an equal sign. So let me rewrite them. I can rewrite these in the following way: half E square plus B square. I can write it as half mod of E plus I B square. That's just rewriting. And this Poynting vector E cross B, I can write it as 1 by 2I E plus IB star cross I'm just rewriting it. E cross E is 0, B cross B is 0, only the cross term is there, and that is exactly this. Clearly, these objects are invariant under discrete duality, because goes to minus E goes to B, B goes to minus B. This is invariant. E goes to minus E goes to B, B goes to minus E. Though that's an extra minus sign, but the order is changed in the cross product. And by writing it this way, one sees that not only discrete duality, they are also unchanged under duality rotation. Invariant under duality rotation. E plus IB going to E phi E plus I. So the physical quantities that describe electromagnetism, which means energy density and the momentum density, are invariant under this duality rotation for pure gravity, for pure electromagnetism, when there are no electric charges. Now this is an exercise. Show that the Lagrangian density that's what Lagrangian density of pure electromagnetism is, E square minus B square. Hamiltonian density is E square plus B square, Lagrangian density is E square minus B square. And the quantity E dot B transform under this duality rotation, they transform into each other. And they transform as a doublet. under duality rotation. That is half E square minus B square and E dot B transform as cosine 2 phi minus sine 2 phi, sine 2 phi, cosine 2 phi. Do this exercise. I'll give you a little hint so that you can do it very quickly. I mean, you can do it in very different ways, but I'll give you a hint. And you can do it then in 2 lines. And the hint is, you know how this transforms our duality. Picks up a phase E phi. Take square of this and see how it transforms. And then see how the real component transforms and the imaginary component transforms. The real component of this object is Lagrangian density and imaginary component is E dot B. Clear? Its real component is twice the Lagrangian density, so maybe if you want you can take half of this. That's exercise number 1. Exercise number 2. Show that E dot B is a total divergence. Right, E in terms of gauge potential A, and B in terms of gauge potential A, and then show. You know how to write F mu nu as gauge in terms of gauge potentials. Therefore, you know how to write E in terms of gauge potentials. Therefore, you know how to write B in terms of gauge potentials. Write it in terms of gauge potential and show that is a total divergence. Okay. This was Maxwell's theory. It's U1 theory. It so happens that even in non-abelian, so let's say, okay, non-abelian, say SUN gauge theories, there's a corresponding object E A dot B A. Now this dot is in the space-time vectors. In the non-abelian gauge theory, you have the corresponding F mu nu A, which can be written as a matrix like that. Three components can be identified as non-abelian electric field, 3 components are non-abelian magnetic field, and take this quantity. This quantity turns out to be a total derivative even in non-abelian gauge theories. Is a total divergence And quantities which are total divergences in some sense carry information only about the topology of the manifold on which they are defined, because they pick up only the properties. If I take a, they are described completely by the properties. If I integrate these objects by the properties of the theory at infinity, because total divergence can be converted into, integral of a total divergence can be converted into an integral over a surface surrounding the region in which that total divergence is calculated. So it calculates, it captures the properties of the fields on that surface. It has nothing to do with what is inside. Whatever is to inside, that property must get to the boundary, and the way it gets to the boundary, that's the only property it will measure. So in that sense, it in some sense senses only the topology. So these are therefore topological currents. We'll understand them better when we analyze them. So E dot B is a total derivative and is at topological density. Further, in Euclidean space-time, its 4 integral with proper normalization is always an integer. So what have we done? We will understand maybe on the way these things better, but right now we want to register only some of their properties. But what we have seen is that, and they are given a name. So this object is given a name in non-abelian theory. Instanton number density. So what have we learned? We have learned that the Lagrangian density and instanton number density form a doublet under duality rotation. Now this was pure electromagnetism. A is summed over, yes. So this was a discussion of pure electromagnetism. Now, can we extend this discussion with electromagnetism with sources? We have no sources here, no sources for electric charges. Now, clearly that's Maxwell's theory. If I put sources, add sources to this, electric sources to this, that gives me Maxwell's real full-fledged Maxwell's theory. But real full-fledged Maxwell's theory does not have this duality invariance. So, full-fledged Maxwell's theory which means rho E non-zero and electric current non-zero does not have a duality invariance. That's because we don't have any magnetic currents and magnetic source charge density. Nature we don't have that. But somehow let's put in a magnetic charge density and magnetic currents in Maxwell's theory and see what properties it has. So we modify Maxwell's theory or add to Maxwell's theory magnetic charge density, so rho m and magnetic current I rubbed off those things earlier, but from your notes you will see, so pure electromagnetism divergence of E plus IB was 0. And now let me put electrical charge density plus magnetic charge density. And the second equation was curl of E plus IB minus, I think, well, okay, equal to d by dt of E plus IB and electric current and magnetic current. Maxwell's theory is with this 0 and this 0. There is no magnetic charge density and there is no magnetic current. And clearly these equations are covariant under duality rotation. E plus IB goes to E, the phase times E plus IB, rho E plus I, rho M goes to phase times rho E plus I, rho M, J E plus I, J I M goes to I phi, J E plus I. So what do we learn? We learn that if we want the duality property that we had for pure electromagnetism, also when electromagnetism has interactions, matter is interacting with matter, then we have to include both electric matter as well as magnetic matter. So, electric charge density and magnetic charge density. But that is not Maxwell's theory. Now, let me rewrite the same thing in covariant notation. So, covariant notation. Covariant notation was in terms of field strengths, F mu nu. The Maxwell's equations or the equations of this theory in covariant notation is that d mu of F mu nu is where J nu E is the zero component is rho E and space component is the electric current. We are working in natural units, C equal to 1, right? And then we had another equation for pure electromagnetism. This was 0. But now we have magnetic sources. So, this would be where and I can combine these into one complex equation. And duality rotation in this notation is simply F mu nu plus I, F mu nu tilde goes to E phi F mu nu plus I, F mu nu tilde J E mu plus I, J M mu goes to E phi J mu E J mu M. Clear? And discrete duality, let me just go back to discrete duality was phi equal to minus pi by 2. That gives me F mu nu goes to F mu nu tilde and F mu nu tilde goes to minus F mu nu. The same what we wrote earlier for pure gravity, and sources J electric mu goes to J magnetic mu and J magnetic mu goes to minus J electric mu. So, to remind you that In this theory, what we have done is we have introduced magnetically charged sources. But there are no magnetically charged particles that are seen. So if this description has to have a meaning, then we will say that maybe there are magnetic charged particles in the nature, but we have not seen them so far. We have not seen them so far means that they perhaps, if they are very heavy, so they have escaped detection. So they are very heavy, or for some other reason they have some special property that they cannot be so easily observed. So they have escaped detection. So we can take that perspective and understand what the structure of this theory is. But remember, we have not seen a magnetically charged particle, single magnetically charged. We have seen magnets, but we have not seen isolated magnetic charge in nature. But if there is some magnetically charged particle in nature, then it has very strong consequences on some of the properties of particles we already know. For example, particles like electron, positron, proton, it has very serious consequences of what their charges have to be. So let me discuss that now. Is that existence of a magnetically charged particle in nature necessarily means electric charge must be quantized in nature. Existence of a magnetically charged particle in nature implies that the electric charge must be quantized. What do we mean by must be quantized? That electric charge that we see in nature must be in terms of some basic unit times an integer, always. A common basic unit times an integer. Somehow we see that property in nature. The physical particles that we know of have 1 unit of electric charge or minus 1 unit of electric charge, or 0, or 2 units of electric charge. So existence of a magnetic charge monopolar. Okay. Existence of a magnetic charged particle in nature implies this is due to quantum consistency of theory with such objects, such magnetically charged objects. It's a quantum theory that tells us this, which means, and the quantization is in the following way. If E times G is some 2 pi times n, where n is 0 plus minus 1 plus minus 2, which means n is set of integers, and G is the magnetic charged particle with magnetic charge G. Now let's try to argue that this is true. Proof of this statement. Consider a magnetic monopole somewhere in nature, somewhere in the universe, somewhere maybe in the room somewhere. So somewhere in some region, in some region. The magnetic field due to this monopole is B, is the magnetic charge times the radial vector 4 pi r cube. That's what magnetic field to a magnetic monopole is. Now, to avoid the issues related to fact that what happens at r equal to 0, the origin, that's where the magnetic field is, let's consider a region which is greater than the origin. So this is the field somewhat away from the magnetic monopole. So in some neighborhood of size r0 and beyond. Now we ask the question, this is the magnetic field of a monopole. Can I write it as curl of a gauge potential? Because that's what magnetic field in Maxwell's theory was. Can I write this magnetic field as curl of a gauge potential? Gauge. Now the answer is that there is no gauge potential which is well defined everywhere. But we know divergence of B is not 0 in our theory, because we have introduced magnetic sources. So the moment you introduce magnetic sources, you cannot write B as curl of A. And if you try to do that, then such an A would not be well defined everywhere, it would be singular somewhere. Anyway, let's go and try to do it and see what the singularity is. So let's go and try to write down an expression for which this is true at least at some places, if not everywhere in space-time. Let's go ahead and attempt to find an A, find such an A. Go to spherical coordinates from x, y, z to r, theta, phi, where x is r sine theta cosine phi, y is r sine theta sine phi, and z is r cosine theta. So you have x, y, z, this is some point, this is r, this angle is theta, take the projection onto the x plane, this is rho, and this angle between x axis and this is phi, and rho is r sine theta. Now, and x square plus y square plus z square is r square, and x square plus y square is rho square, which is r square sine square theta. Let me write down the unit vectors in r direction. Unit vector in r direction is x by r, y by r, z by r. And a unit vector in theta direction is xz by r rho, yz by r rho, minus rho by r. And the unit vector in the phi direction is y rho minus x rho. Now, there are two solutions to this problem. The solution 1, I will call it A vector 1, is g by 4 pi r 1 minus cosine theta divided by sine theta E phi. Is that the A field along the phi direction given by G is the magnetic charge of the monopole, 4 pi r 1 minus cosine theta sine theta. If you calculate the B field for this gauge potential, that's precisely that. G r vector divided by 4 pi r cube. The other one, and we are considering all these for a region little away from the origin. Second solution is, call it A2 minus g by 4 pi r 1 plus cosine theta sine theta exercise. Show that magnetic field for both these is but we said that if we do try to find a gauge potential that has this property, it cannot be well defined everywhere. And why have we have these two solutions now? Are they well defined everywhere? Clearly they are not well defined everywhere. Now let's see why they are not well defined. Look at this solution, solution 1. Theta equal to pi. This is 1, cosine theta, cosine pi is minus 1, so it's 2 by 0. Theta equal to 0 is singular. That is negative z axis, sorry, pi, theta equal to pi. And similarly solution 2, theta equal to 0 is singular. Yeah, but that's little away. So that's, but point is that that's undefined. No, theta equal to 0 is here is 0 by 0, right? So that's fine. No, theta equal to 0 is fine. Theta equal to pi is the problem, and theta equal to 0 is the problem for here. And that is positive z axis. Clear? So we did find a solution for a problem, but the problem is that such gauge potentials are singular along a line starting from the origin. Now if I put a surface, a sphere around origin, so put a sphere around origin, sphere S2 around origin, then A1 is singular on the south pole of S2 and A2 is singular at the north pole. Clear? So if I want to describe magnetic monopole now, field of a magnetic monopole without singularities, then I cannot describe it by one gauge potential. What I can do is I can describe it by two gauge potentials. By choosing one gauge potential to describe it in the upper half part of S2 and other one to the lower part of S2. Clear? So to avoid singularities, we describe the gauge potential for a magnetic monopole in two patches. A northern hemisphere by A1. And A1 was G by 4 pi R 1 minus cosine theta by sine theta E phi. So this is my northern hemisphere and I define it by A1. And this object has singularity at the south pole. But then I don't use this to define the gauge potential in the southern hemisphere. So southern hemisphere, so not northern hemisphere and southern hemisphere I use the second one. Now equator, he says, is shared by both. So at equator I have two of them. So overlapping region is equator. Overlapping region, equator, which is theta equal to pi by 2. Theta equal to pi by 2 circle. Now what happens at equator? Let me see what is the value of difference of the two gauge potentials at equator. What is the value? I have these two answers here. Equator, or maybe let me extend it a little below, a little above, in the neighborhood of the equator. Now remember, what is the grad operator in polar coordinates? That's what is the grad operator in polar coordinates. Now this object, therefore, I can write it as is precisely this. Maybe white 4, 2 pi. I should have a 2 pi. Why did I write 4, right? Is that clear? So the difference is grad of phi, this phi coordinate, or so the difference in the overlapping region difference of these two potentials, or these two potentials differ, these two potentials differ by a gauge transformation, because that's how the gauge transformation of a potential is derivative of some angle, grad of some chi. Gauge transformation by parameter, or by parameter chi phi equal to g by 2 pi phi. But this gauge transformation has a very interesting property, that it is not single valued. In this sense, it is not continuous. This gauge transformation is not continuous, because chi of 2 phi minus chi of 0, which are the same point, phi 0 and phi 2 pi are the same point, the chi differs, and chi differs by g, which is not 0. Clear? So these gauge potentials that we try to set up to describe the field of a magnetic monopole have to be defined in two different separate patches to avoid the singularities. And in the two such patches, the potential that we have in the overlapping region differ from each other by a gauge transformation which is not continuous. Clear? Now let's calculate the magnetic charge for this configuration. How do we calculate magnetic charge? You calculate the magnetic field B and integrate it over a closed surface. That particular S2. So I have an S2 around magnetic monopole. I put a ball around the magnetic monopole. Ball has a boundary S2. Calculate B dot ds on the surface of the circle, this ball. Well, not now this ball I break into two parts, the northern hemisphere plus southern hemisphere. Clear? And now when I break it in northern hemisphere and southern hemisphere, my B phi, I can convert this B as a curl of an A which is well defined A, because in each region I have two different A's. And therefore I can use Stokes theorem in each region. So use the Stokes theorem. This surface integral becomes an integral over the equator. E is the equator, that is this one. Along a loop, this loop on the equator, right? And similarly, I do it in the southern hemisphere. Now this drawing is not very accurate, because how do I do this, make it more accurate, is if I make it this is dotted one, which is, that means it's the other side, and then when I combine this one, this is dotted line, this is the other side, this is inside. So this and this is combined, this and this is combined. So now this is right.
Outward line is northern hemisphere points that way, because when you curl your hand across, you would likely go outside the surface.
Say it again.
Going outward from the northern hemisphere. So
Yeah, It's a flux going out there and going down there the other way, right? So that's why that is what I'm trying to do with these arrows, and to make the sign that the two arrows have to be in opposite orientation, and therefore that's precisely what I've done.
An absolute flip for both of them.
No, there's no absolute flip.
So he's wondering if what you have applied is a left hand.
I mean, this is left hand. This should have been this way.
Yeah, or
It's possible that I don't know. This could be this way, and then this would be this way.
yeah. Does it really make a
It will not make a difference. Well, it will make a difference, I think, if one does it carefully, whether it's whether charge turns out to be plus G or minus G. That kind of it. It will flip this charge. And now, since we have seen what is the difference of these objects, clear? Is that now the electric charge for this configuration is given by the line integral along the equator of del of chi, because this difference is del of chi, and that line integral is simply the value of chi for phi equal to 0 to 2 pi, the difference, and that is G. So, but that was what it was, because the B field that we had written down was the B field due to a magnetic monopole of charge G. So that's what we discovered is the property also of these gauge potentials that we have. So the magnetic charge is well defined. And the gauge potential in the overlapping region differ from each other by a gauge potential, by a gauge transformation, which is completely controlled by the magnetic charge, which is a gauge function with a whose period value is the magnetic, given by magnetic charge. Now, do we have time? Not today, so Monday. Now I think we'll do quantum mechanics with this and then discover that electric charge is quantized.